The last transmission from a submarine that wasn't lost. There's a kind of silence that means nothing, and a kind that means everything, and the trouble is they sound exactly the same for the first several hours. At 2:14 in the morning, a relay station logged a signal. Ordinary, mid-thought, the way a person trails off when they mean to finish a sentence later. Then it just stopped. No distress call, no garble, nothing that would make a technician sit up straighter. For a long while afterward, the frequency hummed the way empty frequencies do, patient and unbothered, as if it hadn't noticed anything was missing. You'd expect a story like this to end in tragedy, and maybe you're already arranging the pieces that way. It didn't. The vessel was fine. It surfaced hours later, crew slightly annoyed, slightly proud, having simply gone somewhere the signal couldn't follow it. Not lost, unreachable. There's a difference, and almost nobody sits with it long enough to notice how strange that difference actually is. Here's the part that stays with people, the part they mention to someone else the next day without quite knowing why it matters. The ocean has swallowed more transmissions than space has. Not metaphorically, literally, mechanically, in terms of raw signal loss. Water absorbs radio waves so efficiently that a submarine a few hundred meters down is, for communication purposes, farther from us than a spacecraft past the orbit of Mars. You can talk to something leaving the solar system easier than you can talk to something under your own boat. That's the thing nobody explains to you, and maybe that's fine, because the ocean was never in the business of explaining itself. I keep turning this fact over, and I'm still not sure I've got the shape of it right. We think of the deep as close because it's ours, because it's underwater we've sailed over for centuries, because a coastline feels like something we already understand. But closeness isn't the same as reachability. A place can sit 15 minutes from where you're lying right now and still be less known to us than the far side of a moon we've never set foot on. Sound moves differently down there. Light gives up almost immediately. Past a couple 100 meters, it's mostly gone. And past 1,000, it's absolute. The kind of dark that doesn't have a texture, that isn't waiting for your eyes to adjust because there's nothing to adjust to. Radio dies even faster. What's left mostly is pressure and the slow arithmetic of things sinking. Somewhere in that arithmetic is the submarine going about its business, utterly fine, utterly cut off, its crew probably not thinking about any of this at all. That's what gets me. They weren't in danger. They were just somewhere our instruments hadn't been built to follow, doing something as mundane as checking a gauge or logging a depth reading, while up on the surface a relay station quietly filed the silence as unusual, and then, eventually, as normal. Maybe you've felt a version of this. Not underwater, obviously, but that specific sensation of being present, entirely fine, and simply unreachable. A phone with no signal in a basement. A room where nobody knows to look for you yet. The particular quiet of being somewhere real, while the rest of the world logs you as absent. It's not the same thing, but it's close enough that something in your chest recognizes it before your mind does. We've mapped 90-some% of Mars in detail you could plan a hiking trip around. We've got contour lines for craters on the moon nobody has ever stood in, and the seafloor, most of it, is still guesswork. Gravitational shadows, sonar pings extrapolated across gaps the size of countries. Somewhere down there are mountain ranges longer than the Andes that no camera has ever seen, sitting in the same darkness that swallowed a submarine's signal at 2:14 in the morning, not for any dramatic reason, just because that's what the deep does. It doesn't hide things, it just doesn't transmit them. I don't think the ocean is trying to keep a secret. I think it's more that nothing down there was built to be heard, and we keep forgetting that not being heard isn't the same as not being there. Pressure. Somewhere inside a single cubic centimetre of seawater, nothing feels unusual. The molecules are doing what they always do, jostling, bumping, indifferent to depth. It's only when you zoom out that the number starts to mean something. At the surface, you're already carrying a column of air on your shoulders, and you never notice, because you were born under it, and your body calibrated itself before you had opinions about anything. Water is heavier. 10 meters down, the pressure has already doubled. By 100 meters, it's 10 times what it was when you waded in. Keep going and the arithmetic stops being gentle. At the deepest point in the ocean, a little under 11 kilometers down, the pressure is over 1,000 times what you're feeling right now reading this sentence. A teaspoon of water down there carries roughly the weight of a small car balanced on a fingernail. Steel groans before it gives. Submersible hulls are built thick and round for a reason. A sphere distributes force evenly, which is the only shape pressure has any patience for. The body, unprotected, wouldn't explode. That's the movie version. It would fold. Air pockets, lungs, sinuses, the middle ear, collapse inward long before anything ruptures outward, because gas compresses and water basically doesn't. There isn't a dramatic failure. There's just less and less space where there used to be some. I think about the fish that live down there and I'm still not entirely sure how they manage it, even having read the explanation a dozen times. Most deep-sea fish have no swim bladder, no gas-filled cavity to betray them. Their tissue is mostly water and fat, which is already close to incompressible, so the pressure has nothing to squeeze. Their cells are packed with molecules called piezolites that keep proteins from folding wrong under crushing force. It's less that they resist the pressure, and more that they've made peace with it, structurally, at the level of individual molecules. Bring one of these fish up fast and it comes apart, not from the ocean's pressure, but from its absence. The gas dissolved in its tissues expands violently as the water above it thins out, and by the time it reaches sunlight it often looks nothing like what it was an hour before, which means strangely the crushing depth was never the dangerous part for these animals. Home was fine, it was the trip toward us that killed them. Trieste went down in 1960, a bathyscaphe with a steel sphere just large enough for 2 men and their instruments, and one of the outer windows cracked on the way. A sound like a gunshot through the hull. Everyone assumed the worst, and they kept descending anyway because turning back at that depth takes almost as long as continuing. The window held, barely. They spent 20 minutes on the bottom, saw a flatfish that startled everyone by existing at all down there, and came back up. You feel this pressure conversation somewhere specific if you slow down enough to notice. A small tightening behind the sternum, the kind you get imagining a held breath that isn't yours. That's not really about the ocean. That's your own body doing arithmetic it wasn't built for, translating a number into a sensation because numbers alone don't land anywhere. What's strange is that the pressure isn't a wall. It's not the ocean saying no. It's just what water does when there's enough of it stacked overhead. Patiently, without any intention behind it at all, the same way gravity has no opinion about the things it pulls down. Somewhere between the surface and the bottom, there's a depth where a human lung would already be behaving like something else entirely, and past that, another depth where the difference stops being measured in multiples of what we started with and starts being measured in something closer to geology. I don't know that I've ever fully sat with how much water is actually on top of that trench at any given moment. Kilometers of it. Not resting there, moving, circulating, entirely unconcerned with the number it's producing near the bottom, a number that would kill nearly everything that has ever walked on land quietly without a sound. Maps of places no one has drawn. Long before anyone thought to measure the ocean, they had already measured the moon. Galileo pointed a telescope at it in 1609 and sketched craters onto paper, mountains and shadows, a whole topography of somewhere no human had ever set foot. It would be centuries before anyone did the same for the floor a few hundred meters beneath a fishing boat. I've come back to this comparison more than once, turning it over the way you'd turn over a coin looking for the mint mark, because it never quite stops being strange. We had rough maps of a body 384,000 kilometers away before we had rough maps of the one thing directly beneath most of the planet's surface. Cartography moved fast on land and slow at sea, and the reason is almost embarrassingly simple. Light doesn't reach past a few hundred meters of water, and cameras need light, and satellites, however clever, can't photograph what's underneath an opaque surface. So the tools had to be indirect. Sonar. Sound sent down, and an answer measured in the time it took to come back, over and over, ship after ship, building a picture one narrow strip at a time. Later, someone realized gravity itself could be borrowed as a mapping tool. A seamount, a mountain rising from the ocean floor, has enough mass to very slightly bend the sea surface above it. The water actually piles up a few centimeters higher over something heavy hidden below. Satellites reading the shape of the sea surface, down to the centimeter, could infer the shape of the seafloor without ever touching it. This is how most of what we know about the deep ocean's terrain was assembled, not by seeing it, but by measuring what it does to the water sitting on top of it. Even with that, the resolution is coarse. Satellite gravity mapping can tell you a mountain is roughly there, roughly this size, but not what it looks like, not what's growing on it, not whether there's a vent field breathing heat into cold water somewhere on its flank. High-resolution mapping, the kind done by ships dragging sonar back and forth in long, patient lines, has covered only a modest fraction of the seafloor in real detail. An international effort called Seabed 2030 has spent years trying to close that gap, and it's still nowhere near finished. Underneath all of this sits the largest single geological feature on Earth, and most people have never heard of it. The mid-ocean ridge system winds through every ocean basin on the planet. Tens of thousands of kilometers of underwater mountain chain, longer than every land mountain range combined laid end to end. It's where new ocean floor is born, magma rising, cooling, spreading outward in both directions like a seam continuously stitching itself. Almost none of it has been seen directly. Most of it has never had a light shined on it at all. Sediment falls the entire time this is happening, a slow grey rain of skeletal plankton and mineral dust drifting down from the sunlit water far above, settling over millennia into layers so fine they read almost like tree rings. If you knew how to read them, if anyone had gone down to look closely enough at enough of it. Every so often a ship finds something that had no business surprising anyone in this day and age, a previously unknown seamount the height of a skyscraper, sitting in water regularly crossed by shipping lanes, simply never noticed because nobody happened to run a sonar line directly over it. It isn't hidden, exactly. It's just that hidden and unvisited turn out to be nearly the same thing down there. There's a version of this story where the moon is the underdog, smaller, colder, farther away, and still somehow better understood. That's backwards, actually. The moon was never the hard one. The fish with a face. Like a lantern. For a second, right before it happens, the water in front of it looks like nothing at all. Then a small light switches on. Not a glow exactly. A pinprick, blue-white, dangling from a stalk that grows straight out of the thing's skull like it was never optional, like the body simply grew a fishing rod because the dark demanded one. This is the anglerfish. Not one species. Dozens. Most of them small, most of them ugly in the specific way that only makes sense once you understand where they live. The light is bacteria, real, living bacteria, housed in a pouch at the tip of the lure, given shelter and sugar in exchange for glowing on command. Nobody designed this arrangement. It was negotiated slowly over millions of years the way most good deals in biology are. Something drifts close, curious maybe, hungry more likely. The light doesn't explain itself and it doesn't need to. Down here, light this deep only ever means one thing is trying to become food for another thing, so the pull is instinctive, older than thought. And then it's already too late, because the mouth beneath the light is enormous, relative to the body holding it, hinged wide, full of teeth, angled backward, so that anything that enters doesn't leave. There isn't a chase, there's a lure, and then there's nothing. I keep sitting with how strange the arrangement actually is once you slow down enough to look at it directly. The predator isn't fast. It isn't strong. It doesn't need to be, because it has convinced the ocean to bring dinner to it. Some of what happens next is stranger still, and it's specific to a handful of these species in particular. In several anglerfish, the male is a fraction of the female's size, sometimes less than a tenth, and instead of hunting on his own in a world with almost nothing to hunt, he bites into her flesh and stays there. Their skin fuses, blood vessels join. Eventually his own eyes and organs degrade, unnecessary, and he becomes something closer to an attached gonad than a separate animal, a permanent sperm bank riding along for as long as she lives. It sounds cruel described that way. It isn't, not really. It's an answer to a specific problem, which is that finding another anglerfish in total darkness across empty cubic kilometers of ocean might only happen once in a lifetime. So once it happens, biology apparently decided not to let go. Almost nobody has seen any of this alive, moving, doing what it does in its own water. Specimens come up in nets, already gone, colour drained, shape collapsed by the pressure difference on the ascent. What we know mostly comes from these ruined bodies and a small number of deep submersible encounters, filmed in cold blue light that isn't really the light the fish would ever produce on its own. The lure goes dark again when there's nothing nearby worth luring. There's no reason to keep the light on. Down there, everything costs energy. And energy is the only thing genuinely scarce. What the trench does to time. It has been falling for weeks by the time it reaches here. A fleck of dead plankton, a fish scale, a grain of mineral dust. Marine snow they call it, and the name is kinder than the thing itself, which is mostly just organic debris drifting down from the sunlit water hundreds or thousands of meters above. It falls slowly, centimeters per second, drifting sideways with whatever current happens to be moving at that depth, taking its time in a way nothing at the surface is ever allowed to. Down in the trench, this falling is the only weather there is. No storms, no tides that matter at this depth, no seasons, because seasons are a function of sunlight, and sunlight gave up long before the water got anywhere near this deep. What's left is temperature barely above freezing, pressure past 1,000 atmospheres, and a slow, continuous rain of the surface world's leftovers. The seafloor receives this rain and does almost nothing with it in a hurry. Sedimentation in the deep ocean happens at a pace that makes glaciers look impatient. In some abyssal regions, a single centimetre of accumulation can represent 1,000 years, sometimes longer, layer settling on layer the way dust settles on a shelf nobody dusts. Some parts of the seafloor down there haven't been meaningfully disturbed in millions of years, not protected exactly, just never worth disturbing, too deep for waves, too dark for burrowing animals in any density, too remote for the geological churn that reshapes shallower ground. It sits. It has always sat. A submersible's headlights are sometimes, quite literally, the first light a specific patch of that seafloor has known since before there were mammals to have built the submersible. I try to hold this idea and it keeps slipping a little, the scale of it. We measure our lives in decades and call that a long time. Sediment down there measures itself in intervals we'd need a geologist's vocabulary to even name properly. And yet things live there, on a completely different clock. Glass sponges in the deep Pacific have been aged by growth rings not unlike a tree's at well over 10,000 years old. Individual animals older than agriculture, older than writing, sitting quietly in the cold the entire time civilizations rose and fell somewhere far above them. Certain deep-sea corals show similar ages. A Greenland shark cruising slowly through cold water at depth may not reach sexual maturity until it's over 100 years old and might live past 400. Long enough that one swimming right now could have been alive before some countries existed. Cold slows metabolism. Slow metabolism slows aging. Down here, biology and geology seem to be running on the same instructions. Do less, take longer, and let that be enough. None of these animals experience this as strange. There's no contrast for them. No surface world to measure themselves against. No decades ticking by in a way that would register as unusual. Time isn't passing quickly or slowly down there. It's just accumulating, undocumented. You've probably heard at some point that we know more about the moon than we do about our own ocean floor. It gets repeated so often it's started to sound like a slogan instead of a fact, and that's worth being a little suspicious of. So here's the actual shape of it. Bathymetry, the science of mapping underwater depth and terrain, has covered most of the seafloor only at low resolution. The kind that can tell you roughly how deep something is over a wide area, but nothing about its texture, its life, its specific shape. High-resolution mapping, detailed enough to actually navigate by, actually study, actually understand, has touched a modest fraction of the total. Real numbers keep shifting as ships keep working, but the gap has never closed, only narrowed slowly against an enormous denominator. The reason isn't mystery, it's money, mostly, and distance, and the specific hostility of the destination. A research vessel costs tens of thousands of dollars a day to operate, and mapping the seafloor properly means moving slowly, in long, overlapping lines across an area that covers most of the planet. Space agencies get headlines and not coincidentally budgets. Ocean mapping gets a much smaller line item year after year, quietly. There's a particular kind of underfunding that isn't obvious until you compare it side by side. Governments have spent enormous sums cataloguing craters on the far side of the moon, a place with no life, no weather, no direct relevance to anyone's daily existence. Meanwhile, a trench a few hundred miles off a country's own coastline can sit essentially unmapped, because it doesn't generate the same kind of public excitement, and public excitement is what tends to move funding. It isn't that the ocean is unknowable. Submersibles exist. Sonar exists. The Seabed 2030 project has spent years trying to assemble a complete high-resolution map of the entire ocean floor by the end of this decade, piecing together data from research cruises, naval surveys, and commercial shipping routes that happen to run sonar while they travel. Progress has been real. It has also been slow, chronically underfunded, dependent on whichever government or institution feels like paying for a particular stretch of water in a particular year. Curiosity follows visibility mostly. You can point a telescope at something and see it change, season to season, crater to crater, and that visibility generates funding, generates missions, generates decades of sustained attention. The ocean floor resists that. It doesn't reflect light back at anything. By its nature, it refuses to be seen cheaply, refuses to make itself worth funding the way a bright object in a dark sky does almost automatically. So it waits. Not patiently exactly. Patience implies awareness. It just sits there, undocumented, the way most things sit when nobody happens to be looking, unmapped not because it's impossible, but because nobody has yet decided it's worth the cost of finding out. The sound that's been going on since 1991. The listening station sits on a stretch of coastline most people couldn't find on a map. One node in a network built during the Cold War for a single purpose: to hear Soviet submarines before anyone else could. Underwater microphones scattered across ocean basins, feeding into rooms full of people whose entire job was distinguishing the hum of a hostile hull from the hum of everything else the ocean makes. Then the Cold War ended, and someone had the good sense to hand the whole listening apparatus to scientists instead of quietly switching it off. In August of 1991, not long after that handoff, the array picked up something nobody had a name for, a sound that rose in pitch, over and over, a long train of narrow climbing tones lasting a few seconds each, repeating, loud enough to be heard across the entire equatorial Pacific. They called it upsweep because that's what it did, and the name is the only part of the mystery anyone managed to solve quickly. At first, some assumed a whale. Whale calls are among the loudest biological sounds on Earth, capable of travelling for enormous distances underwater by riding a layer of ocean called the sound channel, a depth band where temperature and pressure bend sound waves so they travel for thousands of kilometres with barely any loss. It's the reason a call made off one continent can, in principle, be picked up near another. But whale calls vary. Pitch, rhythm, individual signature. This didn't. Researchers found the tone too uniform, too mechanical in its repetition. And by the mid-1990s, the biological explanation had mostly been abandoned. What was left pointed towards something geological, an undersea volcano, somewhere in a remote stretch of ocean between New Zealand and South America. breathing intermittently into cold water. It has never fully stopped. The volume has faded since the early recordings, gradually, the way most things fade rather than end. But the array still catches it, seasonally, peaking each spring and each autumn for reasons nobody has confirmed. Nobody knows for certain whether the seasonal shift comes from something happening at the source or from the way sound itself travels differently through water at different times of year. Both explanations are plausible. Neither has won. I find myself doing the arithmetic without meaning to. That's 30-some years now. 30-some years of a signal rising out of a specific patch of remote ocean, recorded by machines built to listen for something else entirely, still audible, still essentially unexplained, while entire scientific careers have started and ended in the meantime. It's just a sound, a place in the ocean occasionally making a noise. That's all it needs to be, and somehow that's the part I can't quite let go of. Things that live without light. No sunlight has ever reached this particular patch of rock. Not once. Not in all the time the rock has existed, and yet it's crowded here. Tube worms, some of them over 2 meters long, packed together in white casings around a fissure where mineral-rich water, heated by magma below, pours out into the near-freezing deep. The water is thick with sulfur, opaque with it, chemically hostile by any ordinary definition of that word. The worms have no mouth, no gut, no way to eat in any sense you'd recognize. Instead, each one carries a body cavity packed with bacteria, trillions of them, that take the sulfur compounds from the vent water and convert them into usable energy, this same basic conversion that plants do with sunlight, except there's no sunlight involved anywhere in the chain. Chemosynthesis, not photosynthesis. Energy pulled from the Earth's own chemistry instead of borrowed from a star. This was discovered by accident in 1977, when a research submersible exploring the Galapagos Rift found something nobody had predicted. Dense clusters of life clinging to hydrothermal vents, thriving in water that should have been, by every prior assumption about biology, close to uninhabitable. Around the worms move blind shrimp by the thousand, eyeless, navigating instead by heat-sensing organs on their backs, tuned not to light, but to the faint infrared glow the vent itself gives off in total darkness. Crabs pick through the debris. Bacterial mats coat every surface like a pale film, converting chemistry into biomass at a rate that briefly outproduces almost anything happening in sunlit water above. None of this depends on the sun, not indirectly, not eventually, not at any point in the chain. Nearly every other ecosystem on the planet, forests, coral reefs, grasslands, your own body, traces its energy back to sunlight through some number of steps. This one doesn't. It runs entirely on heat and chemistry, leaking out of the planet's interior, a closed loop that would keep functioning even if the sun somehow went dark tomorrow. Some biologists think this looks close to how life first began here, back before there was oxygen, before there was a stable atmosphere doing anything useful, when the planet's own chemistry was the only available source of energy for anything. The event itself won't last. Hydrothermal systems shift, seal over, open elsewhere, over years or decades, and when one dies, the community around it dies with it. No gradual decline, mostly, just an ending. The mineral chimney cooling into something inert, the worms gone within a season, the water clearing. Somewhere nearby, usually, another vent is already opening, the nearer unknown. By now you've been in the dark long enough that your eyes have stopped straining against it. Here's the fact that recasts everything you've just spent an hour inside. As of the most recent dives, 27 people have descended to Challenger Deep, the lowest point in any ocean on Earth. 24 people have been to the moon, walking its surface or orbiting it. More humans have reached the bottom of our own planet's water than have ever reached the one that hangs visibly over it every night. Sit with that for a second, because it runs backward from the intuition most people carry around without examining it. We assume space is the harder frontier, the more exclusive one, the one that costs more in every sense. It did, for decades. It doesn't anymore, not by this particular measure. It quietly stopped being true sometime in the last handful of years, and almost nobody noticed the moment it happened. The submarine from the beginning of this, cut off from its own signal, present and unreachable at the same time. The pressure that would fold a body before it could think to react. The seafloor still waiting on ships that haven't been funded to map it. The fish with the borrowed light. The sediment settling in millimeters per century, patient past any human definition of patience. The sound still rising out of a remote patch of Pacific, seasonal, unexplained, 30-some years and counting. The worms living on chemistry instead of sunlight, indifferent to whether the sun exists at all. All of it closer to you than any spacecraft has ever travelled. All of it underneath boats that cross that water every day, going somewhere else, thinking about something else entirely. We didn't call the ocean the unexplored one for most of history. We called space that. Turns out the unexplored thing was under the keel the whole time. Patient, undisturbed, not hiding, just never quite worth the trip. Somewhere down there, right now, something is falling, slowly, through water that has never once been touched by a beam of sunlight, toward a floor that has been waiting, without any particular hurry, since long before there was anyone up here to wonder about it. The architecture of the abyss. If you were to drain the ocean and stand on the bottom, the first thing that would strike you isn't the darkness or the cold, but the sheer, overwhelming flatness. Past the continental shelves, past the steep drop-offs of the slopes, the earth simply gives up on building mountains and settles into a vast, unbroken plain. This is the abyssal zone, stretching from about 3,000 meters down to 6,000. It covers more than half the entire surface of the planet, making it the single most common landscape on Earth, and yet it is a place almost no human being has ever seen. You would expect an abyssal plain to be barren, a desert of mud and silence. And in a way, it is. But it is a desert built on a timescale that makes human history look like a brief, frantic interruption. The floor here is covered in a fine greyish-brown ooze. If you were to scoop it up in your hands, it would feel like wet flour, but it isn't dirt. It is the accumulated remains of everything that has ever lived in the water above. The silica shells of diatoms, the calcium carbonate tests of foraminifera, the microscopic fragments of creatures that drifted, died and fell through the water column for thousands of years. In some places, the sediment accumulates at a rate of a few millimeters every 1,000 years. When you stand on the abyssal plain, you are standing on time itself, compressed into a fine, featureless powder. But the flatness is an illusion of scale. If you look closely, the plain is littered with rocks. Not just rocks, but perfect, dark, metallic spheres. These are manganese nodules, They look like lumps of coal or smooth black potatoes scattered across the mud as far as the eye can see. They are everywhere. In some areas, they cover the seafloor so densely that there is barely any mud visible between them. What makes them strange isn't just their abundance, but how they form. A nodule starts around a tiny nucleus, a shark tooth, a quartz grain, a fragment of basalt, and then, over millions of years, metals like manganese, iron, nickel, and cobalt precipitate out of the seawater and layer onto it, atom by atom. They grow at a rate of a few millimeters every million years. Some of the nodules sitting on the abyssal plain right now are tens of millions of years old. They are older than the Himalayas. They were forming while the ancestors of modern mammals were still small, shrew-like creatures hiding in the underbrush. And they are entirely inert. Nothing eats them. Nothing uses them. They just sit there, accumulating in the dark, a slow chemical rain that builds a metallic crust over the bones of the deep. When you look at a photograph of the abyssal plain, taken by a deep-towed camera or a submersible, the landscape looks almost alien. It is a monochrome world of grey mud and black nodules, stretching out into a darkness so absolute it feels heavy. There are no ripples, no wind, no weather. The water is so still that the tiny tracks left by a sea cucumber or a brittle star can persist for years, long after the animal itself has moved on or died. It is a landscape that preserves its own history simply by refusing to change. We think of the Earth as a dynamic, churning planet, constantly reshaping itself with volcanoes, earthquakes, and erosion. But down here, in the abyss, the Earth is holding its breath. The tectonic plates are moving, yes, but they are moving at the speed of fingernail growth. The sediment is falling, but it is falling at the speed of geology. It is a place of profound, almost aggressive stillness. And yet, it is not empty. Life exists here, but it is life that has accepted the terms of the environment. It doesn't fight the stillness, it incorporates it. The creatures of the abyssal plain are slow, deliberate, and ancient in their rhythms, moving through a world that measures its changes not in seasons, but in epochs. The Deal vertical migration. There is a movement happening in the ocean right now as you read this that dwarfs any migration on land. It doesn't involve herds of wildebeest crossing a river or flocks of birds darkening the sky. It is entirely invisible from the surface, and it happens every single day, twice a day, like the breathing of a massive unseen lung. It is called the Deal vertical migration, and it is the largest movement of biomass on the planet. As the sun sets and the surface of the ocean plunges into darkness, something extraordinary happens in the water column. Billions, trillions of tiny organisms begin to move upward. They are zooplankton, tiny crustaceans like copepods and krill, along with the larval stages of fish, squid, and jellyfish. They spend their days hiding in the deep, cold waters, anywhere from 200 to 1,000 meters down, where the light cannot reach, and predators that hunt by sight cannot find them. But when the sun goes down, they begin the long ascent toward the surface. They move slowly, swimming against the faint, lingering currents, rising through the twilight zone, through the midnight zone, until they reach the upper layers of the water. There, they feed on the microscopic phytoplankton that have spent the day photosynthesizing in the sunlight. They eat in the dark, hidden by the cover of night, and then, just before dawn, they begin the long journey back down into the depths. This happens every day. Every single day, the largest animal migration on Earth moves up and down in the water column. If you were to stand on the deck of a ship at night and look down into the water with a sensitive sonar, you would see a false bottom rising toward the surface. The sound waves bounce off the dense layer of organisms, creating a shadow that mimics the seafloor. During World War II, Navy sonar operators were deeply confused by this. They would detect a massive solid layer rising from the depths every evening and sinking every morning. They thought it was a new type of thermocline, or a secret layer of the ocean they didn't understand. It took marine biologists a while to convince them that the false bottom was actually alive. The sheer scale of this migration is difficult to comprehend. The biomass moving up and down every day is estimated to be billions of tons. It is a vertical river of life, flowing upward in the dark and downward in the light, and it fundamentally shapes the ocean. By eating at the surface and defecating in the deep, these tiny organisms are actively pumping carbon from the atmosphere down into the abyss. They are a crucial part of the biological pump, the mechanism that regulates the Earth's climate. Without this nightly commute, the carbon cycle of the planet would look entirely different. But from the perspective of the organisms themselves, it is a matter of simple survival. The surface is a dangerous place. It is full of fish, birds, and larger predators that hunt by sight. The deep is safe, but it is empty of food. So they compromise. They risk the dark journey to the surface to eat, and then they retreat to the safety of the abyss to digest. It is a rhythm as old as the multicellular life itself, a silent, massive pulse that beats in the chest of the ocean, completely unnoticed by the world above. The whale fall. When a whale dies, it does not simply disappear. In the open ocean, far from the shallow coasts where scavengers might pick at a carcass, a dead whale becomes an event. It becomes an ecosystem. The body is massive, rich in lipids and proteins, and when it sinks, it falls through the water column like a slow, dark meteor. It takes weeks, sometimes months, for a whale carcass to reach the seafloor. As it falls, it is picked at by hagfish, sleeper sharks, and deep-sea amphipods. But even when it finally hits the bottom of the abyssal plain, there is still a tremendous amount of energy left in the bone and blubber. When a whale fall lands on the seafloor, it creates a sudden localized oasis of plenty in a desert of mud. The first to arrive are the mobile scavengers. Hagfish and sleeper sharks swarm the carcass, tearing at the soft tissue. They are joined by large isopods and crabs. This is the mobile scavenger stage, and it can last for months or even a few years. They strip the body of almost all its soft tissue, leaving only the massive skeleton behind. But the story doesn't end there. The bones, saturated with lipids, become the foundation for the next stage. This is the enrichment opportunist stage. The seafloor around the skeleton becomes thick with organic matter. Worms, snails, and crustaceans that usually struggle to find enough food in the barren mud suddenly find themselves in a feast. They colonize the bones and the surrounding sediment, multiplying in densities that would be impossible anywhere else on the abyssal plain. Then comes the final, and perhaps the most fascinating stage, the sulfophilic stage. As the lipids in the bones break down anaerobically, they produce hydrogen sulfide, a toxic gas. On the surface, this would be a dead zone, but in the deep, it is an invitation. Chemosynthetic bacteria colonize the bones, feeding on the sulfide and converting it into energy. These bacteria form thick white mats over the skeleton, and where the bacteria go, specialized animals follow. Bone-eating worms like the infamous Osedax, or zombie worms, bore into the skeleton with their roots, hosting the bacteria inside their tissues to digest the bone. Clams and mussels that rely entirely on chemosynthesis set up shop around the base of the skeleton. A single whale fall can sustain a complex, diverse community of organisms for decades, sometimes up to 100 years. It is a temporary island of life in the deep sea. When the whale first falls, it is a sudden, violent injection of energy. But as the years pass, it slowly transitions into a slow-burning chemical engine, feeding a community that has evolved to rely entirely on the slow decay of the dead. Eventually, the bones are completely degraded, the lipids are exhausted, and the sulfide production stops. The community disperses, the bones are dissolved by the slightly acidic seawater, and the seafloor returns to its quiet grey flatness. But for a century that patch of mud was a thriving, bustling metropolis, all because a giant died at the surface and decided to sink. It is a profound reminder that in the deep ocean, death is not an end. It is simply a transfer of energy, a slow, deliberate feeding of the dark. The architecture of transparency. In the twilight zone, and extending down into the midnight zone, there is a predator that hunts by looking for the silhouettes of its prey against the faint, down-welling light from the surface. Even hundreds of meters down, there is still a tiny amount of light filtering through the water. If you look up, it is a dim, ghostly blue. If a predator looks up, any solid object will block that light, casting a dark shadow against the brighter water above. To survive in a world where being seen means being eaten, the organisms of the mid-water have evolved a brilliant extreme solution. They have simply stopped being solid. Transparency is the ultimate camouflage in the deep ocean. If you have no pigment, no light-absorbing tissues, light simply passes through you. You cast no shadow. You are invisible. This is why so many creatures in the mid-water look like they are made of glass. Siphonophores, which are colonies of tiny specialized animals working together as a single organism, drift through the water like intricate floating chandeliers made of clear jelly. Salps, barrel-shaped creatures that pump water through their bodies to propel themselves, are completely transparent, looking like nothing more than a faint pulsing distortion in the water. Comb jellies, or ctenophores, are teardrops of clear gel. Their only visible features the iridescent bands of cilia they use to swim, which scatter the light into rainbow colours. But transparency is difficult to achieve. Most biological tissues are opaque because they contain proteins, lipids, and water, all of which have different refractive indices. When light passes from one medium to another, it bends and scatters, which is why flesh looks solid. To be truly transparent, an organism must minimize these differences. They do this by using a lot of water in their tissues, keeping their structures incredibly thin, and using specialized molecules that match the refractive index of the surrounding seawater. Some animals take transparency to an even more extreme, almost unsettling level. Consider the barrel-eye fish, or Macropina microstoma. It lives in the deep twilight zone, and its head is completely transparent. It looks like a clear, fluid-filled dome. Inside this dome you can see its internal organs, but most strikingly you can see its eyes. They are two bright green tubular structures pointing straight up. The fish uses these eyes to look through its own transparent head, scanning the water above for the silhouettes of prey. When it spots something, it can actually rotate its eyes forward to look directly at its target. Then there is the glass squid, with its transparent body and large globe-like eyes, or the transparent jellyfish, whose internal canals and reproductive organs are so faintly pigmented they are almost impossible to see. These creatures are not just hiding, they are living proof of the extreme lengths to which evolution will go to solve a problem. In a world without shadows, the best way to avoid casting one is to become the light itself. They are ghosts of the water column, drifting through the dark, entirely present but utterly unseen, a testament to the strange, beautiful logic of the deep, the brine pools. If you were to take a submersible down into the Gulf of Mexico to a depth of about 1,000 meters, you might expect to see the usual abyssal landscape: grey mud, the occasional sponge, the slow drift of marine snow. But in certain places the seafloor suddenly gives way to something that looks like a shoreline. There is a distinct edge, a beach of white sand or rocky escarpment, and beyond it, a pool of shimmering liquid. It looks exactly like a lake. It has a surface, it has ripples, it even has a shoreline. You could imagine dropping a pebble into it and watching it sink. But you are already underwater. This is a lake beneath the ocean. These are brine pools, and they are one of the most bizarre and hostile environments on the planet. They form in depressions on the seafloor where salt deposits, left over from ancient evaporated seas, are buried beneath the sediment. Over time, the immense pressure of the water above dissolves this salt, creating a brine that is 3 to 5 times saltier than the surrounding seawater. Because it is so dense, it doesn't mix. It stays pooled in the depression, held in place by its own weight, separated from the normal ocean above by a sharp, distinct boundary called a halocline. If you were to fly a drone over a brine pool on land, you would see a flat, salty lake. If you take a submersible into a brine pool in the ocean, you experience something entirely different. As you descend through the halocline, the water suddenly becomes incredibly murky. The refractive index of the brine is so different from the normal seawater that it bends the light, creating a shimmering mirage-like surface. When you cross it, it looks and feels exactly like breaking the surface of a lake on land. You are now swimming in a different body of water, entirely contained within the ocean. The brine itself is toxic. It is anoxic, meaning it has no oxygen, and it is often rich in hydrogen sulfide and methane. It is a chemical nightmare. If a normal fish swims into it, it will instantly go into shock and die, its body preserved by the extreme salinity and lack of oxygen. The shoreline of a brine pool is often littered with the carcasses of mollusks, crabs and fish that wandered in and were instantly killed, their bodies mummified in the toxic brine. But life, as it always does, finds a way. The edges of the brine pools are not entirely dead. Specialized microbes thrive in the toxic soup, feeding on the methane and sulfide. These microbes form thick white mats along the shoreline, and where the microbes go, the grazers follow. Mussels and clams have evolved to live right on the edge of the halocline, their roots extending into the toxic brine to host the chemosynthetic bacteria, while their gills filter the oxygen from the normal seawater above. A brine pool is a stark reminder of how arbitrary our definitions of habitable really are. We think of the ocean as a single uniform environment, but down there, it It is a landscape of hidden valleys, toxic lakes, and sharp chemical boundaries. It is a world within a world, where the water itself can be as alien and hostile as the vacuum of space, and yet, somehow, life has learned to build a shoreline in the dark. The global conveyor belt. When we think of the ocean, we usually think of the surface. We think of waves, tides, and the wind-driven currents that push water across the equator. But these are just the skin of the ocean. Beneath the surface there is a much larger, slower, and more powerful movement of water. It is called the thermohaline circulation, or the global conveyor belt, and it is the circulatory system of the entire planet. This current is not driven by the wind, but by density. Cold water is denser than warm water, and salty water is denser than fresh water. In the North Atlantic, near Greenland and Iceland, the surface water is cooled by the freezing Arctic air. As sea ice forms, it leaves the salt behind, making the remaining water even saltier. This cold, salty water becomes incredibly dense, and it sinks. It doesn't just sink a few meters, it plunges thousands of meters down to the seafloor, flowing southward along the bottom of the Atlantic Ocean like a massive, slow-moving underground river. This deep water flows all the way down the Atlantic, around the southern tip of Africa, and into the Indian and Pacific Oceans. It moves incredibly slowly, creeping along the abyssal plains at a rate of perhaps a few centimeters per second. It takes hundreds, sometimes thousands of years for a single drop of water to complete the journey from the North Atlantic to the deep Pacific. Eventually, in the North Pacific and the Southern Ocean, this deep, cold water slowly rises back to the surface. It is warmed by the sun, becomes less dense, and flows back across the surface toward the Atlantic, where the cycle begins again. This conveyor belt is the reason the Earth's climate is as stable as it is. It transports massive amounts of heat from the equator to the poles. It carries dissolved oxygen down into the deep ocean, allowing life to exist in the abyss. It carries nutrients from the deep back to the surface, fueling the phytoplankton that form the base of the marine food web. But it is also incredibly fragile. If the water in the North Atlantic becomes too warm or too fresh from melting ice, it won't be dense enough to sink. The conveyor belt could slow down or even stop. If that happens, the deep ocean would slowly run out of oxygen. The surface would lose its supply of nutrients. The climate of the entire planet would shift dramatically. We often think of the ocean as a static body of water, a blue expanse that just sits there. But it is actually a massive, slow-moving engine. The water you are looking at on the surface of the Pacific might have been frozen in the ice of the Arctic 1,000 years ago. The oxygen you are breathing might have been dissolved in the water off the coast of Antarctica 1,000,000 years ago. The ocean is not just a place, it is a process. It is a single, continuous planetary metabolism, breathing in heat and exhaling cold, moving in a slow, deliberate rhythm that has kept the Earth alive for millions of years. The Hadal snailfish. Below the abyssal plains, below 6,000 meters, the Earth's crust folds in on itself. These are the Hadal zones, the deep ocean trenches, the Mariana Trench, the Tonga Trench, the Kermadec Trench. They are the scars of subduction, where one tectonic plate is being forced beneath another, plunging into the mantle. The pressure here is immense. At the bottom of the Mariana Trench, nearly 11,000 meters down, the pressure is over 1,000 times the atmospheric pressure at the surface. It is the equivalent of having 50 jumbo jets stacked on top of you. For a long time, scientists believed that nothing could live down there. The pressure was simply too great. The proteins would denature, the cell membranes would fail, the basic chemistry of life would break down. But when we finally sent cameras and landers to the bottom of the trenches, we found something astonishing. There, swimming calmly through the crushing dark, was a fish. It is called the Hadal snailfish, or Pseudoliparus swirri. It is a pale, translucent, almost ghostly creature, looking more like a tadpole than a fish. It has no scales, and its bones are mostly cartilage. It looks fragile, soft, and entirely unsuited for an environment that would crush a steel submarine. But it is perfectly adapted. The snailfish survives the crushing pressure through a remarkable biochemical trick. It produces massive amounts of a molecule called trimethylamine N oxide, or TMAO. TMAO acts as a chemical shield. Under extreme pressure, water molecules are forced into the spaces inside proteins, causing them to unfold and lose their function. TMAO binds to the water, preventing it from entering the proteins and keeping them stable. The deeper the snailfish lives, the more TMAO it produces. It is estimated that at the very limits of where fish can survive, around 8,000 meters, their bodies would be almost entirely saturated with TMAO. They cannot go any deeper because they simply run out of room in their cells for the protective molecule. The Hadal snailfish is the deepest living fish ever discovered. It hunts by using a highly sensitive lateral line system to detect the faint water movements of tiny crustaceans in the dark. It doesn't have a swim bladder, because a gas-filled cavity would instantly implode. Instead, its body is mostly water and gel, incompressible, and perfectly matched to the pressure of its environment. When you look at a video of a Hadal snailfish swimming in the Mariana Trench, it is a profoundly humbling experience. You are watching a creature that is living in an environment that would instantly destroy a human being. It is not struggling. It is not suffering. It is just swimming, going about its day, entirely at home in the most hostile environment on the planet. It is a reminder that the limits of life are not defined by the environment, but by the ingenuity of biology. The deep ocean is not a dead zone. The microbial dark matter. When we talk about life in the ocean, we usually talk about the things we can see. We talk about whales, sharks, coral reefs, and schools of fish. We talk about the giant squids and the anglerfish. But these large visible organisms are just the tip of the pyramid. The vast majority of life in the ocean is invisible. It is the microbial dark matter. In a single milliliter of seawater, about the size of a raindrop, there are roughly 1 million bacteria and 10 million viruses. If you took all the viruses in the ocean and lined them up end to end, they would stretch for 10 million light years. There are more viruses in the ocean than there are stars in the observable universe. These microbes are not just floating there, they are doing the work of the ocean. They are the engines of the global biogeochemical cycles. Every time a phytoplankton dies, it is the bacteria that break it down, recycling the carbon, nitrogen, and phosphorus back into the water. Without them, the ocean would quickly become a toxic soup of dead organic matter, and life on Earth would collapse. But the viruses are perhaps the most fascinating and the most misunderstood. A virus is not technically alive. It is a packet of genetic material wrapped in a protein shell, and its only purpose is to infect a host cell and replicate. In the ocean, Viruses infect bacteria, archaea, and phytoplankton. They kill an estimated 20 to 40% of all marine bacteria every single day. This sounds like a disaster, but it is actually the mechanism that keeps the ocean functioning. When a virus infects a bacterium and causes it to burst, it releases the cell's contents back into the water. This process, called viral shunt, prevents the bacteria from being eaten by larger organisms and instead keeps the nutrients in the microbial loop. It fundamentally alters the flow of energy through the ocean. Furthermore, when viruses replicate, they often make mistakes, incorporating pieces of the host's DNA into their own genetic code. When they infect a new host, they transfer that DNA. This horizontal gene transfer is one of the primary drivers of evolution in the ocean. The viruses are constantly mixing and matching the genetic code of the marine world, driving innovation and adaptation in the dark. We have only sequenced a tiny fraction of the microbial life in the ocean. The vast majority of the species we find in seawater samples have no known relatives. They are entirely new branches on the tree of life, operating with biochemical pathways we don't yet understand. They are the unseen majority, the silent workforce of the deep, doing the essential invisible work that keeps the planet alive. We map the craters on the moon, but we have barely begun to map the microbial universe in a single drop of seawater. The psychology of the descent. There is a specific psychological weight to going down into the deep ocean. It is not just the physical pressure, it is the psychological reality of the environment. When you are in a submersible, descending past 1,000 meters, the light from the surface fades to a dim blue, then to a twilight grey, and finally past 1,000 meters to absolute, impenetrable black. Inside the submersible, the environment is cramped, cold, and loud. The titanium sphere that protects you from the crushing pressure is only a few feet across. You are sitting shoulder to shoulder with the pilot and the observer. The air is recycled, smelling of sweat, ozone, and the faint metallic tang of the electronics. Condensation forms on the cold metal walls and drips onto your shoulders. The only light comes from the small instrument panels and the occasional flicker of the external cameras. But the most profound sensation is the awareness of what is outside. You know that just a few inches away, separated by a few inches of titanium and acrylic, is water that is trying to crush you with the force of 1,000 atmospheres. You are acutely aware of every sound. The hull groans and pops as the pressure equalizes. The electronics hum. The life support system clicks and whirs. Every noise is analyzed, every vibration felt. The pilot sitting at the controls is entirely focused on the instruments. The descent is a slow, meticulous process. You drop at a rate of about 40 meters per minute. It takes hours to reach the bottom. During this time, the mind begins to play tricks. The darkness outside the small, thick acrylic viewport is so absolute that it feels heavy, like a physical substance pressing against the glass. When you turn on the external lights, they only penetrate a few meters into the water. Beyond that, the darkness immediately swallows the light. You are flying through a void, entirely dependent on the machines and the hull. There is a profound sense of isolation. You are cut off from the rest of the world. Radio waves don't penetrate water, so you have no GPS, no internet, no phone calls. You are communicating with the surface via a thin tether, or, in the case of free-diving submersibles, you are entirely alone. The surface world with its sunlight, its wind, its noise feels like a distant memory, a different reality. When you finally reach the bottom and the lights illuminate the seafloor, there is a moment of intense, almost overwhelming awe. You are seeing a place that no human eyes have ever seen. The sediment is undisturbed, the landscape is alien, and the creatures that drift past the viewport look like they belong on another planet. But even in that moment of discovery, the psychological weight remains. You are a visitor here, an intruder in a world that is fundamentally hostile to your existence. You are kept alive only by a few inches of metal, and the ocean is entirely indifferent to your presence. It is a humbling, terrifying, and profoundly beautiful experience. It changes the way you understand your place in the world. The Anthropocene Trench. We like to think of the deep ocean as a pristine wilderness, a place untouched by human hands, a final refuge from the chaos of the surface world. We imagine it as a timeless, unchanging dark, where the only forces at work are the slow, geological movements of the earth and the quiet rhythms of deep-sea life. But this is a comforting illusion. The reach of humanity has outpaced our understanding. We have not yet mapped the deep ocean, but we have already polluted it. In 2019, explorer Victor Vescovo piloted his submersible to the bottom of the Mariana Trench, the deepest point in the ocean. When he looked out the viewport at the pristine, undisturbed sediment of the Challenger Deep, he saw something that did not belong. There, resting on the grey mud, 11,000 meters below the surface, was a plastic bag. It looked like a candy wrapper, fluttering slightly in the faint current. A few years later, in 2020, researchers studying amphipods, tiny, shrimp-like crustaceans, found in the Kermadec and Mariana Trenches, discovered that every single one of them had microplastics in their stomachs. Plastic does not biodegrade. It photodegrades, breaking down into smaller and smaller pieces under the influence of sunlight. But in the deep ocean, there is no sunlight. The plastic that sinks to the bottom simply sits there, or is ingested by the creatures that live in the sediment. It becomes part of the food web. The microplastics are eaten by the zooplankton, which are eaten by the fish, which are eaten by the larger predators. The plastic is now circulating through the deepest, most remote ecosystems on the planet. We have also left other marks. Sunken ships, discarded fishing nets, and industrial waste litter the continental shelves and the abyssal plains. The noise from shipping lanes penetrates deep into the water column, disrupting the communication of whales and the behavior of deep-sea creatures. The warming of the surface water is changing the chemistry of the deep, altering the oxygen levels and the solubility of the calcium carbonate shells of deep-sea organisms. The deep ocean is not a separate world. It is the lowest point on Earth, and gravity ensures that everything that happens on the surface eventually finds its way down. The marine snow that falls to the abyssal plain is no longer just dead plankton and mineral dust. It is a rain of microplastics, chemical pollutants, and the detritus of the Anthropocene. This realization is profoundly unsettling. We have managed to alter the most remote, inaccessible, and hostile environment on the planet before we even fully understand it. We have left our mark in the dark, a permanent synthetic layer in the geological record. Future geologists millions of years from now will find a distinct layer of microplastics in the sediment of the abyssal plains, a clear, undeniable marker of the time when a species from the surface reached down into the dark and changed it forever. The deep-sea mining rush. If the deep ocean is a pristine wilderness, it is also a warehouse. The abyssal plains, particularly in a region of the Pacific called the Clarion-Clipperton Zone, are covered in the manganese nodules we discussed earlier. But these nodules are not just interesting geological curiosities, they are incredibly rich in metals. They contain high concentrations of manganese, nickel, cobalt, and copper. These are the exact metals required to build the batteries for electric vehicles, the wind turbines, and the solar panels that are supposed to save us from climate change. As the demand for these green metals skyrockets, the mining industry is looking to the deep sea. The nodules on the seafloor are incredibly rich, much richer than the ores found on land, and they are just sitting there, waiting to be picked up. There are no trees to clear, no indigenous communities to displace, no soil to ruin. It seems to the mining companies like the perfect solution, but the reality of deep-sea mining is far more complex. The machines being designed to harvest these nodules are massive tractor-like vehicles that will crawl across the abyssal plain, vacuuming up the nodules and the top layer of sediment. They will crush the nodules on board, separate the metals, and pump the remaining sediment and mud back into the water as a massive plume. The environmental impact of this is largely unknown, but it is likely to be catastrophic. The abyssal plain is a slow-moving, fragile ecosystem. The creatures that live there grow incredibly slowly, reproduce rarely, and live for centuries. If a mining machine destroys a patch of the seafloor, it could take hundreds, if not thousands, of years for the ecosystem to recover. The sediment plume, injected into the water column, could smother the filter-feeding organisms for miles around, blocking their gills and suffocating them. The noise and the light from the mining operations would disrupt the behavior of deep-sea creatures that have evolved in total darkness and silence. We are currently standing on the precipice of a new industrial revolution, and we are about to start it in the dark. The International Seabed Authority is currently drafting the regulations for deep-sea mining, but the science is lagging far behind the technology. We do not even have a complete map of the seafloor, let alone a comprehensive understanding of the ecosystems that live there. We are rushing to mine the abyss to save the surface, sacrificing the unknown for the known. It is a profound irony. We are willing to destroy a world we have never seen, to build a future we are not sure we can sustain. The deep ocean is not just a resource, it is a complex, ancient, and fragile system. Once we start tearing it up, we may never know what we have lost. The acoustic daylight. In the deep ocean, light is useless. The sun's rays are absorbed within the first few hundred meters, and beyond that the darkness is absolute. But sound is a different story. Sound travels through water nearly 5 times faster than it does through air, and it can travel for thousands of kilometers with very little loss of energy. In the deep ocean, sound is not just a way to communicate, it is a way to see. This is the concept of acoustic daylight. Many deep-sea animals do not have eyes, or their eyes are highly modified to detect the faintest traces of bioluminescence. Instead, they navigate and hunt using sound. They emit clicks, pulses, and low-frequency hums, and they listen to the echoes that bounce back from the seafloor, from prey, and from the topography of the water column. The ocean has a specific layer, called the SOFAR channel, sound fixing and ranging, where the temperature and pressure combine to create a natural waveguide. Sound waves that enter this channel are trapped, bouncing between the layers of warmer and colder water, and can travel across entire ocean basins. A sound made in the SOFAR channel off the coast of California can be heard off the coast of Japan. This means the deep ocean is not silent. It is a cacophony of sound. There is the low-frequency rumble of earthquakes and undersea volcanoes. There is the cracking of icebergs calving in the polar regions. There is the complex, haunting songs of the whales, which can travel for thousands of miles. There is the clicking of shrimp, which is so loud it can interfere with sonar. And there is the biological noise of the deep-sea creatures themselves, communicating, hunting, and navigating in the dark. For a deep-sea predator, the world is not a visual landscape, it is an acoustic one. They can see the shape of the seafloor, the density of the water, and the movement of prey through the echoes of sound. It is a completely different way of perceiving the world. We are visual creatures, dependent on light to understand our environment. The creatures of the deep ocean are acoustic creatures, dependent on vibration and pressure. When we send our submersibles into the deep, we are entirely blind. We rely on our lights to carve out a tiny sphere of visibility in the dark. But the animals down there do not need our lights. They already know exactly where they are and exactly what is around them through the invisible, omnipresent web of sound. The deep ocean is not a silent void. It is a loud, complex, and vibrant acoustic landscape, and we are just beginning to learn how to listen to it. The cold seeps. When we think of life in the deep ocean that doesn't rely on sunlight, we immediately think of hydrothermal vents, the black smokers, the towering chimneys of sulfide, the tube worms, and the blind shrimp. They are the most famous, the most dramatic, and the most visually striking examples of chemosynthesis. But they are not the only ones. Scattered across the continental margins, along the edges of the deep ocean basins, there is another type of oasis. These are the cold seeps. Unlike the hydrothermal vents, which spew superheated, mineral-rich water from the magma below, cold seeps are exactly what they sound like. The water that seeps out of the seafloor is the same temperature as the surrounding deep ocean, just a few degrees above freezing. But it is rich in a different kind of chemistry, methane and hydrogen sulfide. These seeps occur where there are large deposits of organic matter buried in the sediment, or where there are vast reservoirs of methane hydrate, frozen methane, trapped beneath the seafloor. As the sediment shifts, or as the pressure and temperature change, the methane and sulfide slowly leak out of the seafloor. The environment around a cold seep is very different from a hydrothermal vent. The vents are violent, explosive, and short-lived. A black smoker might only be active for a few decades before it seals up and dies. The cold seeps are slow, steady, and incredibly long-lived. They can seep for thousands or even millions of years. Because of this stability, the ecosystems around cold seeps are very different. Instead of the fast-growing, short-lived tube worms of the vents, the seeps are dominated by massive fields of mussels and clams. These bivalves host chemosynthetic bacteria in their gills, converting the methane and sulfide into energy. The seeps are also home to vast fields of orthogenic carbonate, rocks formed by the bacteria as a byproduct of their metabolism. These carbonate rocks form hard, rocky outcroppings on the soft sea floor, providing a substrate for deep-sea corals and sponges to attach to. A cold seep is a slow-burning engine of life. It is not the dramatic, explosive birth of a hydrothermal vent. It is the steady, quiet exhalation of the earth. It provides a stable, long-lasting oasis in the deep, supporting a complex, diverse community of organisms that have evolved to rely on the slow, steady bleed of chemistry from the seafloor. It is another reminder that the deep ocean is not a single, uniform environment, but a mosaic of different habitats, each with its own unique chemistry, its own unique rhythm, and its own unique form of life. The evolutionary time machine. The deep ocean is often described as a museum, a place where ancient creatures have been preserved in the cold, dark, high-pressure environment, unchanged for millions of years. We call them living fossils. The coelacanth, the frilled shark, the horseshoe crab, the giant isopod. They look like they belong in the Paleozoic era, and in many ways they do. But the term living fossil is a bit of a misnomer. It implies that these creatures are lazy, that they have stopped evolving, that they are relics of a bygone era. The reality is much more interesting. These creatures are not failures of evolution. They are its ultimate successes. The deep ocean is one of the most stable environments on the planet. The temperature is constantly near freezing. The pressure is immense, but it is constant. There are no seasons, no weather, no ice ages, no dramatic shifts in sunlight. The environment has remained largely unchanged for hundreds of millions of years. In a stable environment, there is very little pressure to change. If an organism is perfectly adapted to its environment, any mutation that changes it is likely to be detrimental. The frilled shark is perfectly adapted to hunting in the deep cold water. Its eel-like body, its extendable jaws, its hundreds of needle-like teeth, they are exactly what it needs to survive. There is no advantage to changing. So these creatures are not stuck in the past. They are perfectly optimized for the present. They have been evolving, but they have been evolving to stay exactly the same. They are the ultimate conservatives of the biological world, holding on to a body plan that has worked for hundreds of millions of years, while the rest of the planet has undergone dramatic, violent changes. The deep ocean is a refuge. When the surface of the Earth was scorched by asteroids or frozen in global ice ages, the deep ocean remained stable. The creatures that lived there survived, while their relatives on the surface went extinct. The deep ocean is not just a place, it is a time machine. It preserves the history of life on Earth, not in rocks, but in the flesh and blood of the creatures that swim through the dark. When we look at a frilled shark, we are not looking at a relic. We are looking at a survivor, a creature that has found the perfect solution to the problem of existence and has simply refused to change it. The unseen currents. When we think of currents in the ocean, we think of the surface, the Gulf Stream, the Kuroshio Current, the great rivers of water that flow across the surface, driven by the wind. But beneath the surface there is another type of current, one that is entirely invisible from above, but carries a tremendous amount of energy. These are the internal waves. Internal waves occur at the boundary between layers of water of different densities. In the ocean, the water is stratified. The warm, less dense water sits on top of the cold, denser water. The boundary between these layers is called the pycnocline. When the tides pull the water over the underwater topography, like seamounts or ridges, it creates a disturbance at this boundary. This disturbance propagates as a wave, but it is a wave that travels entirely underwater. These internal waves can be massive. In the open ocean, they can have an amplitude of hundreds of meters, meaning the water at the boundary moves up and down by hundreds of meters as the wave passes. But because the wave is entirely underwater, There is no sign of it on the surface. The surface might be perfectly calm, while hundreds of meters below, a massive wave is rolling through the deep. Internal waves are incredibly important for the physics of the ocean. As they travel, they eventually break, just like surface waves on a beach. But when they break, they do it deep inside the water column. This breaking mixes the water, bringing cold, nutrient-rich water from the deep up toward the surface and pushing warm, oxygenated water down into the depths. This mixing is a crucial part of the ocean's circulation, helping to distribute heat and nutrients around the globe. For the creatures that live in the deep, internal waves are a source of food and energy. As the wave passes, it brings a pulse of nutrients and organic matter from the surface down into the twilight zone and the abyss. It creates a temporary current, a surge of water that the filter feeders and the predators can take advantage of. The internal waves are the hidden weather of the deep ocean. They are the storms and the winds of the abyss, shaping the environment, mixing the water, and driving the rhythms of life in the dark. We cannot see them from the surface, but they are constantly moving through the ocean, a silent, powerful force that connects the surface to the deep. The surface tension. After hours in the dark, after the pressure, the cold, the silence, and the awe, the submersible begins its long ascent back to the surface. The ascent is just as slow as the descent. It takes hours to rise back through the water column. As you rise, the darkness slowly begins to change. The absolute black of the abyss gives way to a deep, midnight blue. Then, as you pass through the twilight zone, the blue begins to lighten. You start to see the faint, ghostly shapes of the mid-water creatures drifting past the viewport. The bioluminescence flashes and fades, a silent fireworks display in the gloom. Then you hit the thermocline. The water temperature begins to rise, the pressure on the hull begins to ease, and finally you see it. The surface. It doesn't look like much at first, just a shimmering silvery ceiling above you. But as you get closer, you can see the texture of it. The ripples, the waves, the way the light from the sun penetrates the water and dances across the hull of the submersible. When you finally break the surface, the hatch is opened and the air rushes in. It is warm, it smells of salt and diesel and wind, and it is overwhelmingly, beautifully bright. The sunlight is almost painful after hours in the dark. The noise of the surface, the wind, the waves, the engine of the support ship, the voices of the crew is a deafening roar after the profound silence of the deep. You climb out of the sphere, your legs shaky, your eyes squinting against the light. You are back in the world of the sun, the world of the air, the world of the living, but you are changed. You have been to the bottom of the world. You have seen the architecture of the abyss, the ghostly transparency of the mid-water, the toxic lakes of the brine pools, the slow, steady exhalation of the cold seeps. You have felt the crushing weight of the water, the profound isolation of the dark, and the incredible, stubborn persistence of life in the most hostile environment on the planet. The deep ocean is not just a place, it is a perspective. It is a reminder of how little we know and how much there is left to discover. It is a reminder that the Earth is not just a rock with a thin layer of water on top. It is a complex, dynamic, and deeply mysterious system, and we are only just beginning to understand it. We look up at the stars and wonder what is out there. We build telescopes and send probes to the edges of the solar system, searching for life, searching for answers. But the answers and the life are also down here, right beneath the keel of the ships that cross the surface every day, in the dark, in the cold, in the crushing pressure. The ocean is waiting. It is not hiding. It is just waiting for us to look. And when we finally do, we find that the unknown is not empty. It is full of life, full of mystery, and full of a strange, quiet beauty that defies description. The surface tension is broken. You're back in the light. But a part of you will always be down there in the dark, drifting through the abyss, listening to the slow, steady heartbeat of the deep,